Let's have a look at some circles now. So the first thing is, what is a circle? It's a set of points on a plane that are equidistant from a fixed point, its center. So a circle basically is a line. And the definition of that line is that every point on that circle is the same distance from the center. And that distance, as we know, is the radius. And here in geometry it's defined as the line segment from the center of the circle to any point on the circle. Now, the radius is a specific type of line. We know it as half a diameter. And what is a diameter? A diameter is a line that goes from edge to edge of the circle through the center. It is a particular type of chord. A chord is a line segment that joins any two points on a circle. So if you draw a straight line through a circle, that's called a chord. When it goes through the center, it's the diameter. We look at a circle and we take out a piece of pie, as we usually call them, that's actually called an arc, a sector. The arc is the piece of the circumference on the sector, and then we have this part here, which is made up by two radii. So an arc, or a sector, has an arc and two radii. Then we have tangent here, and a tangent is a line that touches a circle at one point only. Okay, moving on from that. This is one of the theorems you did for your junior circle, or junior cycle, getting confused between junior cycle and junior cert now. Okay, this is one of the theorems you did where you said the angle at the center is equal to twice the size of the angle on the circle when you're talking about the same arc. So what they mean is that if you have a sector like this, you draw an arc from B to C and then go draw two radii into the center, it creates an angle. If you draw two chords joining up together at point A from B and C, you create this other angle up here. The angle here up at A, so BAC, is half the size of the angle here, which is BOC. That can be quite handy when solving some problems, because sometimes you get a situation like this. We have our center here, our arc here, so this is the arc that the lines are on. We could draw our angle up here to B, or we could draw the angle up here to D. Both of these, the angle ABC and the angle ADC, are both on the same arc AC. So that means that even though they look different, this angle here at B is the exact same size as the angle at D. Moving on to our cyclic quadrilaterals. What is a cyclic quadrilateral? Well, you know quadrilateral is a four-sided shape. And if it's cyclic, it means it's inside a circle. So we have a four-sided shape inside a circle. What's so important about that? Well, it has a handy characteristic that the opposite angles in a cyclic quadrilateral add up to 180 degrees. Can be quite useful to know. Now, this is sometimes called angles in semicircles, and you'll often see it written as an angle in a semicircle. So you're only looking at the half of the circle that has this triangle in it. So what we're saying is that if you have a triangle in a circle and the hypotenuse of this triangle is your diameter of the circle, by default the angle out here is always going to be 90 degrees. Moving on to tangents. Characteristic that you have to remember here is that tangent is always perpendicular to the radius at the point of contact. So if you have your radius here, your tangent forms a 90-degree angle. Same here. You have a tangent and a radius, and that's always a 90-degree angle formed there. Always.